Hi class, we are moving on to chapter 4. Chapter 4 covers very abstract ideas that will be unusual to you guys. Just power through it and things will get easier. So we're going to start off with chapter 4.1, discussion about subspaces. Okay. Later on chapter 7 we'll talk about actual vector spaces, which is an extension of this idea of subspaces. So let's start off with the definition. A subset S of R to the n, or notation wise, we say S is a subset of Rn. So the subset notation can either have this bar under it or it could not. With a bar beneath it, it means a proper subset. Without a bar, it means improper subset. We're not going to get into the difference between the two of those. They're not necessary for what we need to concern. I'm going to keep the bar here. I think your book does not, but it's possible so a proper subset means that S is basically equal or equivalent to Rn or smaller than it in size, right, or dimension. So S could be Rn itself, and then Rn is a subset of itself, so that's fine. So that's really what the improper versus proper subset notation means. So we're just going to kind of stay with this notation just because we don't really need to worry about if it's proper or improper, so we'll just keep the proper subset notation. So a subset of S from henceforth will be noted as such. Okay, so when you see this symbol, that means we're talking about S being a subspace, right, of Rn, or a subset. Sorry, it's a subset. It's a subspace if the following conditions are true. Okay, so first is that the zero vector has to be inside of this subset. Okay, for every vector u and v that is inside of my subset of Rn, if I add those two things together, they will still be inside of that subset. Okay, meaning that this subset is closed under addition. Okay, so if I take two items inside of this space and I add them together, I stay within that space. Okay, I cannot add things and get somewhere else. Okay, for every vector u in S and R being a scalar value, R times u is also in S. So I am closed under scalar multiplication. So if you notice, these conditions are pretty much identical to what we do for proving something as a linear transformation. Although we're not doing transformations, we're talking about objects inside of Rn. Okay, so I have to have the zero vector, I have to be closed under addition, and I have to be closed under scalar multiplication. Now the only difference is that in our definition for linear transformation, we did not have this zero vector notation. A lot of you guys are trying to throw that in there. While it is true, that is not what we were using to prove a linear transformation, right? So again, note that the conditions that you need to verify a subspace is identical to those needed to verify a transformation is linear, with the addition of the inclusion of a zero vector. Okay, so not only do these have to remain true, but we're adding in that the zero vector has to be inside of my subset also. Okay, if these three conditions are true, then our subset S of Rn is a subspace of a larger vector space, which we'll get into in chapter 7. Okay, so let's do an example. So for this example, so again, I said that this chapter is very abstract. So a lot of the proofs that we're going to do are abstract proofs. A lot of the examples we're going to do are abstract ideas. There's a lot of theorems in this chapter. There's not a lot of concrete examples. There are, but there's not a lot. So again, you have to put on your thinking hats for this section because we're thinking outside of the box. Okay. So for this example, we want to verify that S, being the set containing the zero vector, is a subspace of Rn, right? So we want to verify that this set is a subspace of Rn. Okay, so here's my proof. So first addition, okay? Obviously, the zero vector is already inside of the space, so I don't have to show that that's true because that's already true. But for addition, let's say we have two vectors, any two vectors in S. So again, I can never say, hey, I have this exact vector and this exact vector. They have to be abstract vectors. But luckily for us, our abstract vectors here are always the zero vectors. So if I have two vectors in S, then that means that U and V are both zero vectors. Okay? So if I add U and V together, I'm going to be adding two zero vectors together, and I will get out a zero vector, which is inside of my set. So if I take two things in S and I add them together, I will get something that is also in S. Okay? Therefore, S is closed under addition. For scalar multiplication, let's take something in S, we'll call it U, and a real valued scalar. Okay? This can be any value. Then U is the zero vector, because that's what things in S look like. And R times the zero vector, right? Any multiple of this zero vector is just going to get you the zero vector. Okay? And that is also what things in S look like. Okay? So therefore, S is also closed under scalar multiplication. Therefore, S equaling the set containing the zero vector is a subset of Rn. Subspace of Rn. Okay? And proof. So just like with linear transformations, showing that R times U plus V equals the distribution of the scalar across the addition, RU plus RV, being in S, is enough to show that S is closed under addition and scalar multiplication. So what that means is I would have to show that this is in S and that this result is also in S. So just like for the linear transformations, this is another shortcut that we could use to take out these two steps and combine them into one single step. Okay. It's a little different, however, because I have to show that this is in S and that this is in S also. They both have to be things in S. Okay. So let's do an example. I'm not going to do an example of the shortcut. I'm just doing another example. However, yeah. So brand new example. I'm not redoing the last one. So let's consider the set S, which is the set of vectors in R2, A, B. So these are things in R2. As you can see, they're vectors that have two elements, such that the vectors that are in R2 and a squared plus b squared is less than or equal to 1. So what this means geometrically is that they are within the unit circle, right? Because these are what things inside of a unit circle look like. But we don't really need to know that in order to show whether or not this is a subspace of R2 or not. It helps, it obviously will help, but I'm not providing a graph here for you, right? So that would have been left up to you to understand what this looks like geometrically. So the question is whether or not this is a subspace of R2 or not, okay? So this is, again, basically the unit circle, okay? So here's our proof, okay? So let's take V equals 1, 0. So right now, this should be a hint to you because I'm pulling out a very specific example. You cannot prove something by using a specific example. A specific example can only be used as a counterexample, which means that since I'm pulling out a specific example, I have to now show that this is not a subspace. So what I'm going to do is I'm either going to show that it's not closed under addition or it's not closed under scalar multiplication, right? This is actually not closed under either. I only have to show one of those properties don't hold, okay? If I was doing a proof, I could not choose a specific vector. I would have to choose a vector AB such that a squared plus b squared is less than or equal to 1, and then do math on that to show whether or not it's closed under addition or scalar multiplication, okay? So again, an example can only be used as a counterexample. You can never choose a specific example to prove something is true. All you're doing is showing that it works for that specific example. If you're doing that, I'm not giving you points for that, okay? So just a heads up if you haven't figured out by now. So here, if I take the vector v is 1, 0, then 1 squared plus 0 squared is 1, which means that that is a vector inside of S. Okay. Therefore, v is a vector that is inside of this space. Consider r equals 2, or really any other scalar that's larger than 1. If I multiply r times v, I will have a vector that is not in S, right? Because if I were to square this, I'd get 4 plus 0, which would then be larger than 1, so it would not be in S. So what I showed is that this is not closed under scalar multiplication. Okay, but I could have chosen a vector, I could have shown it's not closed under scalar addition as well, because I could have just chosen, I don't know, the vector, any other vector really, okay? It doesn't really matter which one I choose, it wouldn't have worked, okay? So therefore, S is not closed under scalar multiplication is what we have shown here with a counter example, right? And since it's not closed under scalar multiplication, that means that S is not a subspace of R2, okay? End proof. So again, just to reiterate, to show something is not true, a counter example is all that is necessary, okay? So let's get into a few theorems. So pretty much everything you're going to have to do in this section, you're going to have to verify through proofs. There's not really, hey, calculate this, calculate that. There's a couple of things that we'll get into towards the later end of this video. But for most things in this section, in this chapter really, you're going to be showing through proof, okay? So theorem. Let's say we have a set of vectors in Rn. So each of these has n elements, and there are m of them. Okay. Then let's say S is the span of these m vectors. Okay. So this space that these vectors generate, right? Because remember, span is a generating set of vectors. It creates a space. The space created by all the possible linear combinations of these vectors is a subset of Rn. Okay. So theorem. Say you have an n by m matrix, which we'll call A. So that n by m matrix can be made by creating these vectors into a matrix, right? Then the set of solutions to the equation A times x equals 0 is a subspace of Rm. Remember, this is m rows, m equations, n columns, right? So I know I guess I messed up here and I put a regular old R and not my nice fancy R, but they are the same R. Okay, so apologies. I guess I didn't code this one in correctly. Okay, but it's the same space. It's still the same Rm space. So this subspace has a very special name. It's called the null space of A. You will hear this term very often for the remainder of the course. It's an important subspace. There's a couple of important ones. This is one of them. Okay. We call the null space of A null of A. Okay. So again, this is not a value. This is a space, right? Like R2 is a space. R3 is a space, right? This is a subspace of a system of equations. Okay, it's basically, the easiest way to think about this is the set of all vectors that when you plug it into your matrix equation, go to the 0 vector, right? It's basically all of the vectors for your particular system of equations that get sent to the 0 vector when you plug it into this linear transformation, or this it's not really a linear transformation, but it's a vector, a matrix equation. Okay. So let's do an example. So let's consider the matrix A. We'll just have it super easy. 1, 2, 3, 4, 5, 6, 7, 8, 9 down the columns, right? Then to find the null space of A, I need to set up this equation. A times x equals 0. Okay. So I can throw it straight into an augmented matrix, because at this point, we know that that's what this looks like as an augmented matrix. Okay. I could also solve this a few different ways. I could try to find the inverse of this and solve it that way, right? We can use Kramer. There's a lot of things that we can do, but it actually turns out that this is not linearly independent. Okay, so we actually cannot solve this using an inverse because there is no inverse for this matrix. So we're going to throw it into our augmented form. We're going to reduce it down. Remember, at this point, I'm fine with you guys just plugging into your calculator, whatever you have, and just telling me that this is the reduced form. So if I throw this into the reduced row echelon form, which is a unique form, you can see that you have a free variable here for x3. Okay, so if we write the set of solutions, right, the general solution for this, x3 is free, x2 is negative 2x3, and x1 is x3. Okay, and then we put this as a linear combination, as we typically do. Oops. Okay, then I have x equals x3, 1, negative 2, 1. So what this means is all vectors that have this form get sent to my 0 vector. My null space is generated by this set of vectors. In fact, this only single vector. Okay, so any constant multiple of this, right, which is x3, makes it a constant multiple. Any constant multiple of this vector, if I were to plug it into this matrix equation that I have, I will always get out the 0 vector. So my null space is generated by this vector. So remember, it's the set of vectors, it's the set of vectors of the span of the vectors that you have, right? So the span of these vectors. So the span of this vector is my null space of this equation. Okay, or of this matrix, I should say. So remember what I said over here, okay? The null space is a subspace, okay? Is this vector x a subspace of R3? Well, yes it is, okay? Because the null space is a subspace, okay? So, proof. The set x is the set of vectors that look like this multiplied by any scalar value, right? x3 is a scalar value. It's the same thing as the span of this vector, which is what I just repeated like 3 or 4 times, right? So any constant multiple of this is in the span of this vector. And that's also equal to the null of A for this matrix A that I have. Okay, this is still the same example. We're just expanding the idea, right? Therefore, the set containing this vector x is a subspace of R3. Okay, so I didn't even really have to prove that. Like, this is just a one-line proof. It's very nice, but it's given by a theorem, right? You can just say yes, due to this theorem, the null space is a subspace. Therefore, the set of this vector is a subspace of R3. Okay. Now maybe you're like, yeah, I definitely wouldn't have thought about that. I would have tried to do that how you just showed me how to do it. Well, let's do it that way, right? Let's do an alternative proof. Let's do this by showing the closure under addition and then closure under scalar multiplication. In fact, we can do it all at once, remember, by showing that this is in S and that this is in S as well, right? Or my space. So let's go ahead and do this proof. Okay. All right, so let's start our proof. Let S equal the set of vectors x, where it's just one vector, such that x has the form some scalar times 1, negative 2, 1, right? The set that we had here. Here, x3 is a scalar. So let's say we have 2 vectors in S and 3 constants, right? A, B, and R. I have 3 constants here because that's how many I'm going to end up needing. So remember, I need 2 vectors because I'm going to add them together. And I need 3 scalars in this case because I'm showing that my vector here is multiplied by a scalar. So for each of these vectors I have, they need to be multiplied by individual scalars. And then when I show the closure under scalar multiplication, I'm going to need that 3rd scalar. Okay, so really I'm just doing this a little bit more difficultly than I need to. Really I just need to take this 1, negative 1, this 1, negative 2, 1 vector. I don't really need this x3. I'm just showing you what it would look like if we did include it. But honestly, like if I was actually doing this, myself to turn something in, or like, at a higher level, I would not include this x3, right? I would not expect you guys to include this scalar here. It doesn't really matter because, I would really say the set S, if I'm showing that something is a subspace, I can say S is the span of this thing, and then I actually wouldn't need to include this scalar at all, right? But I'm just going off of what we got here as the end result from my solution set. So I'm including it in here in the proof. Okay, so again, if I said S was the span of X, where X was 1, -2, 1, this would be redundant, right? Because I'm showing that these two things are equal, because remember, X3 can be any value, right? So I could have just replaced this with a span instead, and then I wouldn't need 3 scalars. I would need just the 1. So I'm making it a little bit harder for myself, but it's really just to show you guys a little bit of variety and a little bit of flavor. Because I said before, your artistic side in math really should come out in the proof process. Okay, so some proofs are pretty straightforward. There's going to be other proofs, as you'll see, where you can be very, very creative, right? So this is where the creativity in math comes from. It is not from knowing how to multiply in some fancy way, right? So this is where the artistic side really should start to show. So let's say I have a vector u and v, then u looks like some scalar times my vector, right? So this is what things in S look like, right? A scalar times this vector. So u is a scalar times that vector. V is going to be the same thing. It's going to be a different scalar multiple times this vector. In fact, a and b can be the same, or they can be different. It doesn't matter. They're generic values, right? They're just generic scalars. So note that if a is 0, okay, then u is 0, because that's the way it works, right? And if u is 0, then that means that 0 is inside of S. Okay, so that means that my subspace, or my subset at this point, because it's not a subspace yet, contains the 0 vector. Okay, so it does have the 0 vector. So that's one of the 3 things. Okay, so the next thing I need to do is show closure of addition, and then closure of scalar multiplication. And again, I can show those 2 things at the same time, which we will do here, right? So if I have R times U plus V, okay, then that's going to look like R times my U plus my V, okay, which gets me R times U plus R times V, right? And R times A plus R times B pulled out gives me my scalar, gives me my vector. So I have a single scalar here because I was able to factor out the 2 constants, or you can think of it as I factored out the common vector. Either way, I have my vector times a scalar, and that's what the things in S look like, right? Since R times A plus R times B is a scalar value, I have a scalar times that vector that all the things in S look like. So this is something that is in S. Okay, and since R of U plus V is equal to RU plus RV, they're one and the same. And I showed that both of those things, by just doing a little bit of math, are things that are in S. So that shows that it is closed under scalar multiplication and addition as well. Therefore, S is a subspace of R3, right? So that would be the alternative method, something that I would have expected you guys to do if I had asked you to show that this is a subspace of R3. Okay, I would not have expected you to notice, like, oh, it's a null space, and we just had a theorem that said the null space is a subspace, therefore it's a subspace. I would have expected you to go ahead and do the full proof, because that's kind of what we're conditioned to do at this point. Although at this point, I would have taken either one of these proofs would have been equivalent, right? So again, 2 different proofs that show the exact same thing. And the only way that I know that this is true is, again, because of the way that I found this vector in the first place, right? I created it by setting this vector equal to, this matrix equal to 0, and solving it down and finding what all vectors that go to 0 look like. Okay. All right. I hope that wasn't too confusing for you guys, and you're familiar with a lot of this stuff from the linear transformation portion, right? So again, therefore, the null space of A, my matrix I had before, is a subspace of R3. 3. Let's do another theorem. We have actually quite a few theorems from this point on, okay? So that was kind of like half of the section, so we have like another half left where we'll talk more about null space and some other fundamental spaces, particularly what's called the row space and the column space as well, although we don't get into column space really. Okay, that's more for, I think, 4.3 or so. Say we have a linear transformation from Rm to Rn. So again, number of rows, number of columns. If we had a matrix for this, it would be n by m, right? Rows for, last in the transformation notation, columns first, right? So this linear transformation is the set of vectors x that are in Rm such that the transformation of this vector goes to 0. So let's say that that's the set I'm interested in, right? So this is a set of vectors that I'm pulling from my linear transformation. This is called the kernel, okay? It's very similar to the null space. It's all of the vectors that I can plug into my linear transformation and get out the 0 vectors. We call that the kernel. Here in this previous example, it was all the things in my matrix equation that when I multiply it times a, go to the 0 vector. Very, very similar in that it's still a times x and it's still equaling 0. It's just that here I'm considering this a matrix, and here I'm considering this as a transformation, right? So I would be, my transformation is given by a transformation matrix. That's why it's related to each other. But again, I think of transformations as functions, whereas stuff that I do on matrices are just things that I'm doing on matrices, right? So we're kind of separating the two, and these are, it's the equivalent side of the coin, basically, right? One is just for matrices, one is for transformations. So for a matrix, we call it the null space. For a transformation, we call it the kernel of T. If any of you guys code and do computer stuff, you should be familiar with this term kernel. It pops up in computer science quite often, okay? We notate the kernel of T as ker of T, okay? So again, null of A and ker of T basically are the same thing. One is for linear transformations. The other one is just applied to a matrix equation. Again, remember, linear transformations and matrix equations are pretty much the same thing, okay? Curve T is essentially the same as null of A, again, right? But in writing, null space is for matrices and vectors, and kernel is for linear transformations. They are the identical thing, though, and they represent similar things. So both represent the set of vectors x, that result in an output of the 0 vector 0 when A is multiplied times your input vector x, okay? So here's an image for the kernel, because again, kernel represents more of transformations, which we consider as functions. So here is your domain, Rm. This is where you're coming from. This is where you're going to. This is your range. Your transformation takes things from your domain and sends them to your range, okay? All the set of vectors inside of your domain that when you plug them into your transformation go strictly to the 0 vector is inside of what we call the kernel, okay? So again, the entire domain, see this big outer little line here? Your entire domain gets mapped to this range, okay? Now it's very possible that range, the range of the transformation is not the entire space Rn. That's why it is not the entire space of Rn here, right? It's a small subset, subspace. In fact, we'll talk about that as well, the range being a subspace as well, okay? The things that I plug in that go to 0, strictly only to 0, are called the kernel, right? So all the things in here are only going to go to 0. All the things in here, when I plug them into my transformation, will go to this set of things here, okay? So hopefully that makes this image make sense to you guys a little bit. The kernel of T is a subspace of Rm. We've actually just shown this earlier, right? We showed that the null space of A is a subspace. So that should make sense to you right here, even if the notation doesn't. And the range of your transformation is also a subspace of Rn, okay? Or I'm sorry, not Rm, of Rn, right? The range of T is a subspace of Rn, as I said before as well. The linear transformation given by the transformation matrix A, where A is basically these column vectors. There's m of them, right? And the span of these vectors is going to be your range of T. Okay, so again, the transformation here is given by these column vectors A1, A2 to AM, right? And the span of those column vectors is the range, which we have talked about before. We talked about in chapter 2, right? Next theorem. If we have a linear transformation from Rm to Rn given by T of x equals Ax, right? So A, again, is our transformation matrix. A in this case is n by m because this is my rows and this is my column, right? Then the kernel of T, right? So everything that this transformation sends to 0 is equal to the null space of A. So everything that this transformation matrix as a matrix would send to 0 as well if it was a matrix equation, which it is because that's what a linear transform is, right? So the kernel of T, the transformation itself, is the same as the null space of A, the matrix that provides the linear transformation, okay? So here's another theorem. Say again, we have a linear transformation from Rm to Rn. Then the kernel T equals the 0 vector if and only if T is 1 to 1. And this should make sense because when we were talking about being 1 to 1, right? 1 to 1 meant that for our system of equations, that everything was linearly independent. And what does it mean to be linearly independent? It means that the only solution that you have when setting something equal to 0 was the trivial solution, when all of your variables are 0. That's all that this thing is saying again. It's just saying it in the form of transformations and being 1 to 1. So again, the only way for your A matrix to send everything to the 0 vector, right? Or, I'm sorry, the only way for everything that gets sent to the 0 vector by your transformation being only all zeros itself, right? Basically the trivial solution is if that matrix is linearly independent, or another way of saying that, your transformation is 1 to 1. Okay, so that's what this theorem is saying. It's saying things that we know already, but in the form of what it would mean under the verbiage of linear transformation. So again, this is not something new. You just got to think about it in a different way now, right? So everything that the transformation sends to 0 is only 0, the 0 vector itself, if and only if this is linearly independent, meaning that T is 1 to 1. Okay, so I talked about the big theorem before. I think I've talked about it once or twice. We have added hell of stuff to this thing now, so we're going to talk about it now, including all of the things that we brought in. Okay, so again, I'm not going to, every time we add something to the big theorem, I'm not going to go over the big theorem, but I will stop and pause every so often, every few sections, and be like, hey, we've just added like 3 or 4 things to this thing, so let's talk about it. So I do talk about it when we bring them up, like for instance, in the determinant section, I said, hey, the determinant being non-zero means x, y, and z, right? But I didn't throw it into the big theorem for us yet. So we've just added quite a few things. So we're just going to update that now here, okay? So the big theorem, we have a couple of things. Let A be a set of vectors, okay? So there's n of them, and each of these n vectors have n elements. They all have Rn, Rn, okay? And let's say I create a matrix out of these vectors, okay? So each of these now are column vectors. We're going to call that matrix this form of A. So I have a slightly cursive A here for the set of vectors, and this A is for the matrix that's formed from that set of vectors. So again, this A should be n by n because there's n of them and they all have n elements. Okay. Also, let's say we have a linear transformation from Rn to Rn. So again, the transformation matrix here will be n by n. And let's say our transformation matrix is given by that matrix that we had here, A, that is made up of the n element column vectors from this set A. So you see how they just kind of feed into each other? So again, we've talked about things being vectors, we've talked about things being matrices, and we talked about things being linear transformations, and we've kind of done so all in their own houses. So what we're doing here in linear algebra is we're showing that all three of these things, they're really just the same thing. Whether it's a set of vectors, whether we're putting those into a matrix, whether we're calling that matrix a linear transformation, or we take that linear transformation and we take its columns and then turn it just into a set of vectors, they're all the same, right? It all feeds into each other. Okay? Then the following are equivalent, meaning if one of these are true, all of them are true. This also means that if even one of these are false, all of them are false as well. Okay? So, if the set of vectors here is linearly independent, meaning you now have n vectors all in Rn being linearly independent, okay? Or this matrix right here is a linearly independent system, okay? The set of vectors here will also span Rn if they are linearly independent, because there are n vectors in Rn that are linearly independent, so they span the entire space of Rn, right? If this is true, then this is true. If this is true, then this is true, as long as there are n vectors in Rn, right? For every b that is in Rn, right? So for every vector you can ever think of inside of Rn, there exists a unique. That's what the exclamation point here means. It means unique. This backwards E means there exists. So there exists a unique vector x in Rn such that A times that vector x equals b. So let's break this down. What does this mean? It means that for every ax equals b that I have, b is any vector, A is the matrix formed here, okay? There's always a solution to it. And there's always a unique solution. There's only one solution, meaning I will never have an infinite solution sort of case, and I will never have a no solution case. I will only have a single solution present, a unique solution, okay? For every b inside of Rn, okay, my range, there exists a unique vector in my domain such that if I multiply my transformation or my matrix A times that unique vector, I will get out that b that I'm interested in, okay? T is onto this transformation made by this matrix A is going to be onto, which coincides with this b here, that A spans Rn because my range here is Rn, so T will be onto. T will be 1 to 1. That coincides with this A, all of these vectors being linearly independent, right? So A and B is the equivalent to D and E, but in the linear transformation world, okay? C is also equivalent to the D world, right? So this matrix equation is equivalent to D in the transformation world, right? Here, this matrix A, the transformation matrix, this matrix made of these column vectors, is going to be invertible. So if A is linearly independent, it is also going to be invertible. So again, remember, if any one of these is true, as long as I'm n by n, all of these are true, okay? The kernel of T is only the 0 vector. And again, this aligns with this linearly independentness of A, and it aligns with this E of the linear transform, of the linear transformation. Okay. Oops. I have one more to add. The last one is that the determinant of A is not equal to 0. So again, this is literally my favorite one right here because it's super easy to check. I always check if I have a square matrix, is my determinant 0? If it's not, well, then that means a lot of things for me, right? It means that I have an inverse. It means that if it's a linear transformation, that my transformation is one-to-one, that it's onto, my space spans Rn, and that I'm linearly independent. It also means I always will have a unique solution to this matrix equation. Okay, I never really talked about the kernel of T too much, but it does let me know, that I'm linearly independent, which means that the only thing that goes to the zero vector is the zero vector, right? So again, my favorite is the determinant of A, because that's my check. I just, find the determinant real fast. Is it 0? No. Boom. That means all of this stuff is true, okay? Which is very, very useful, especially if you're doing proofs or you're, when this stuff is true, your system is really easy to work with. When these things are not true, you probably have to do some extra work, right? So that's why I like the determinant. It's really easy. It's a fast check, okay? Hope this has been helpful to you guys. See you on the next video.